This is part 6 of our revision series. I have only one chapter here, semiconductor electronics or semiconductor devices. Okay. Uh, See, I think basic diodes and transistors are covered, and then the logic gates are covered in semiconductor electronics. But I think the recent CBSE textbook, they have removed transistors. I don't know whether they're going to ask questions this year or not, but I think last year there were few questions on transistors. Okay, so I'm not really sure whether you will get questions on transistor, but anyway, I think the questions on diodes are more common than the questions on transistors. Okay, so the higher chances of getting questions on, let's say, diodes and logic gates. Okay, so but we will look at few questions, not many. Okay, so can you answer this question? Very good. Yeah. So they operated high voltages. Again, even if we have not studied semiconductor devices chapter, we should answer this because we know all electronics are operated at very low voltages. Okay, so very good. Okay, so can you answer this? See, in conductors, okay, when temperature increases, the positive ions they oscillate more vigorously. Okay, so the conduction is because of the free electrons, so their movement is restricted when temperature increases because of the, let's say, vigorous oscillation of the positive ions. So because of that, the resistance increases in conductors. But when it comes to semiconductors, actually the question is more on availability of the free charge carriers. Okay. So first of all, we don't have many free charge carriers in, let's say, semiconductors. Unless we dope it, we don't get those free charge carriers. So when temperature increases, I think the covalent bonds rupture and then you get electron hole pairs. So you actually get more free charge carriers. So the resistance, you can say that the resistance actually goes down because the availability of free charge carriers increases. Okay. So the answer is B. Okay. So can you answer this? So very good. A is correct. See, ionization energy is the minimum energy required to remove that valence electrons, right? I mean, in this case, uh, if you take, I think you must be knowing about this from your chemistry. Okay, so carbon has the highest ionization energy. That is why carbon, even though the valency is 4 for each of these elements, carbon is not a semiconductor, or it's not used as a semiconductor. Okay. That's the reason. Okay, so can you answer this? Okay, so that's right. So here I think you have that result. Okay, so the number of holes into number of electrons in an extrinsic semiconductor. Okay. Is equal to square of the number of let's say free charge carriers or like either holes or electrons in an intrinsic semiconductor. So here since we are doping with a pentavalent element, the charge carriers, the majority charge carriers are electrons. Okay, so this Ni is given. So Ne, how do I get Ne? Ne will be for 1 million, you will get 1 electron. Because there's so many atoms, if you remove 1 million, I think the number of electrons would be 5 into 10 to the power 22. Okay, so that you can substitute here. So the number of holes is Ni square, which is 2.25 into 10 to the power 32 divided by 5 into 10 to the power 12. Sorry, 22. So this is correct. Okay, so can you try this question on diodes? Okay, so here, which of these diodes are in reverse bias?
Second one.
The second one is in reverse bias. So they're ideal diodes, so we don't have to worry about the potential barrier. Otherwise, they normally give potential barrier. Sometimes they may not give the potential barrier. Okay. So for what is potential, I mean, what you can do is whenever they say the diodes are not ideal, you can imagine that you have a battery which is opposing the flow of charges. Okay, just as a like way of solving the problem. But here, you know that the second diode is in reverse bias mode. So when they say ideal, the potential barrier is 0. Okay, so I don't have to worry about that. So either the diode is conducting or it is not conducting. In forward bias, it conducts, and then in reverse bias, it does not conduct. So that means this path is cut off for us. So that means the current is actually flowing only in the outer loop. So 150 and then 50, these are in series. So the total resistance is 200. So the current through the battery will be applied voltage by resistance. So how much is this? This will be 0. I think 0.02.
Yeah.
Okay, so the answer should be D. Okay, so try this. So very good. So that is correct. So now that they have mentioned the potential barrier, and again, if they don't say that it is not ideal, well, they say that if it is not, what am I saying? If they mention that the diode is, let's say, not ideal, okay, if that word ideal is not there, you should consider 0.7 volts. Okay, so here you can say that, okay, I have some opposing potential of 0.7. So what is available? Okay, so 2 volts is available. So 2 by 100. So that's 20 milliamperes. Okay, so try this. You have a Zener diode there. Okay, so if you recall the diode characteristics, so when you apply a potential, okay, and then try to measure the current. So till I think 0.7, assuming we are using a silicon diode, till 0.7, you don't get any current. After that, current sharply rises. Okay, so this smooth curve. But if you reverse the voltage, you don't have like current. But I think after some time, the current suddenly shoots up in the reverse direction. Okay, so in the reverse bias, there is something known as this breakdown voltage. Okay, so these Zener diodes are specially fabricated diodes which operate in reverse bias. Okay, so they can actually allow large amounts of charge to flow through. They can bear large currents without, uh, let's say, altering the potential difference across them. Okay, so when the question says, okay, the potential difference across the Zener diode is 5 volts, that 5 volts is maintained there. Okay, so that 5 volts will be there here. Okay, so if that 5 volts is there, and then these two ends and these 2 points are at the same potential. So the current through 1 kilo ohm would be 5 by 1 kilo ohm. So that is 5 milliamperes. Now, if I take the Zener diode, if you look at the Zener diode, 5 volts is getting dropped across the Zener diode, right? Now 2 volts is available for the 200 ohm resistor. Okay, so what will be the current here? 2 by 200. So that is 10 milliamperes. Now, if I use the junction rule, so 10 milliamperes is coming towards this junction. Out of that, 5 milliamperes went in the other direction. So what current goes through the Zener diode? The remaining, which is 5 milliamperes. Okay, so the answer should be B. So you understand this?
Yeah.
Okay, so try answering this question. So let's talk about this. I think this is a very important question. You say AC voltage. Suppose if I look at the AC signal here. Okay. So the voltage looks something like this. Now this 220 is RMS, right? Whenever they say 220 volts, that is RMS. So what is the peak voltage? The peak voltage is 220 root 2. You know that, right? So the peak voltage will be root 2 times the RMS voltage. Now, till the voltage reaches peak value, the diode is in forward bias mode. Okay, so because the diode is in forward bias mode, the capacitor keeps getting charged. Okay, so because the capacitor gets, let's say, charged, what will happen? The charge will go till the voltage of 220 root 2 is applied, right? So the potential difference would be 220 root 2. So after that, what will happen? Once, if you look at it, 220 root 2, once you get that, uh, between these 2 points, you can imagine that you have 220 volts. Now, if you are applying a smaller voltage, okay, so if you apply a smaller voltage and the voltage drops, the diode will get into reverse bias mode. You understand? So there will not be any charge flow. Okay, so that 220 root 2 will be there. You're okay?
Yeah.
Yeah. Okay, so try answering this question. Yeah, so depletion region and the barrier height, both they decrease. Correct. Okay.
B.
Try
The
answering.
answers.
Yeah, try answering this question.
No, it said answer is B for the previous one.
Oh, is it?
Yeah.
1 second. No, 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 no. I think my mistake. Answer is C actually. Because the depletion region goes down, the width also decreases, and the barrier height also decreases. The answer should be C. So try answering this question. So let's say if I take, so how do you quickly verify such things?
Assume output, I guess. Like
Okay,
1
so
0.
yeah, okay. So let's say if I assume A is 1 and then this is 0, 1 and 0. So what do we get here? I think 1 and 0, this is
1.
AND gate. So you should actually get, yeah, 1. And then you're getting 1 and 1, so you should get 0 here, and then this should be 1, so you should get 0, so you should get 1. Okay, so A and B, okay, so you're getting 0, or yeah, I think this looks okay. I think that verification is okay. You can verify for other inputs. Oh, saying AB prime. So that means you'll have to verify the other things also. Okay, so what do? We better put a table. Okay, so yeah. So let's put a table and then check. I think these things should be easy. So you have to patiently verify. So if I have 1 and 0, I'm getting 1. So let's say if I take 0 and 1. Okay, so let me erase these things. Let's try for this. So if this is 0 and 1, so what do we get here? We get 1 here, right? And then here also we get 1. And then here we get 1. So we are supposed to get 1, but we will get 0. Okay, so let's verify with the other options. So we are getting 0. And then let's say we'll have to verify for 0, 0, and then 1, 1. So let's do that. So let's try 0, 0. See, these questions, I think you must attempt them by verifying, of course, carefully. That, so if I have 0, I should get 1 here, and then I should get 1 here, and this is 1. So I'm supposed to get 1, but I'll get 0. Okay, you're okay there? So we are getting 0 here, and then now verify the last one. Take 1, 1 here. Take 1, 1. So that will be 0, and then this is 1, and this is 1. So should get 0. Okay, so now C matches, let's say A and B. Let's say for 1 and 0, I should get, let's say 0. I should get 1 here. I think 1 we are getting. So 0 and 1. Okay, so 0, I should actually get 1. So this is actually not true. So I think this is, let's verify this. 1 and let's say 0. So that means it will become 1, and then we are getting 1. Okay, so 0, and then this becomes 0, we are getting 0. So I think, yeah, this is okay. So try answering this question. So right now, don't worry. I mean, if the input signal looks something like this, the output signal will be amplified, but it will be 180 degrees out of phase. Okay, so this is input and this is output. So just keep in mind that there is a phase difference of pi radians. Okay. Okay, so try answering this question. Nice. So here, because the conductivity is increasing, the electrons are able to move from valence band to conduction band. So the energy of the photon is definitely greater than the uh, energy gap. Okay.
Mm.
So if you use that 1240 electron volt nanometer divided by wavelength in nanometers, so this is the energy of the photon. So what are we getting here? I think this is around 0.55.
Mm.
Okay, so you cannot really remove electrons from let's say A, B, and D. So C should be correct. Very good. Okay, so try answering this question. I forgot to mention that, but this is last year's mains question. So I said, I mean, this year CBSE does not have transistors,
Mm.
but this question was there last year in mains. What you should remember is the input characteristics are between the current in the base and the voltage across the base. Okay, so you have current in the base, and then voltage across the base will consist of that input characteristics. Output characteristics like current in the collector. I think you know this, right? And the voltage across CE. Okay, so this is taken as the output. Now, if you recall the output characteristic, or let's say you might have seen there's a curve for output characteristic. So it looks something like this. Okay. So the output voltage when it drops to zero, so that is when you get maximum current in the collector. Okay, so that means I will just say that here, whatever current I have, I see. Okay, so once I have maximum current, okay, so VCE becomes zero. So just keep that in mind. Okay, so VCE becomes zero. So VCE becomes zero. I have VCC minus IC RC is zero. So that is when I have maximum collector current. So this is 5, and then IC RC is given as 1 kilo ohms. So IC comes out to be how much? 5 milliamperes. Okay, so because IC is 5 milliamperes, and then current gain is given. So beta DC is IC by IB. So IB will be 5 milliamperes divided by 200. I think that should give you 25 micro amperes. So I can eliminate C and D. Now, but how do I get the input voltage? So we are trying to find the voltage between, let me show those nodes. Okay, so we want the voltage between these 2 points. Okay, now IB into RB. So if I calculate this, so IB is 25 microamperes. RB is given as 100 kilo ohms. So if I multiply 25 micro into 100 kilo, so I'll get 2.5 volts. Okay, so there's a drop of 2.5 volts. And again, across B and E, there is another drop of 1 volts. So that should be 3.5. 2.5 plus 1, it should be 3.5. So B should be the correct answer. Yeah, I think you can say it's actually easy if you know the let's say how transistors actually function. They're actually nicely explained in CBSE textbook. Do you have the old CBSE textbook or the new one?
I don't think, I mean, I do have all of this in the textbook. Like, they
You do
didn't
have all these. I think you
take
better
it out.
revise them. Yeah,
Yeah.
because they might ask even this year. Okay, so try answering this question. CBSE textbooks are very well written. See, here, let's say before overturning. Well, overturning, they're just reversing the polarity. Before overturning, the barrier potential of germanium is zero point 0.3. It is less. So that means the upper path is of low resistance. Okay, so low resistance path, and the lower path is of higher resistance path. So the well, you should let's say the chargers somehow know that. Okay, so they take the least resistance path.
Mm.
So that means the charges will not flow in this direction. So that means your silicon diode is not effective. Okay, so now because of that, if I take the barrier potential of germanium diode, it is 0.3. So V naught would be 12 minus 0.3. So that is 11.7. Now if I reverse it, okay, so if I overturn the germanium diode, okay, so if I connect it like this, now the germanium diode gets into reverse bias mode.
Mm.
Okay, so the charges will not go there because now that will be path of high resistance. Okay, so this is anyway zero grounded. So we can ignore the germanium diode now. Okay, so if I ignore the germanium diode, only silicon diode is effective now. Okay, so if it is effective and then it has a barrier potential of 0.7, so this will be 11.3. So what is the difference between them? The change in the voltage
4.4.
is 0.4. You understand this?